All right. So what we got yesterday is we defined the magnitude of the force. So the magnitude of the force, and again, if I did this, this would be magnitude of the force, that if I were dealing with a single charge, where this is the charge, this is the strength of the magnetic field. Oops, there we go. This is the velocity. And then this is that angle in the field. So it's going to be maximum if I'm perpendicular to the field. So we also said that if I have x's, that my x's are going to be into the page and dots are coming out of the page. And then we showed a variety of videos yesterday to kind of give you an idea of what was happening. Now, unless we're doing a GC mass spec or something else, most of the time we're dealing with a wire. So I'm going to put a wire here into my magnetic field. And when I put my wire in, we can either have the current going this direction or we can have the current going that direction. And depending upon our current, because remember we talked about the right-hand rule, and if I have my current, if I'm going with this direction of my current, I'm going to put my thumb along the current and I'm going to rotate into the page. And if that's the case, if I'm applying a current here, I'm going to get a magnetic field around this wire. And that was, we talked about that being Ampere's law. And basically what Ampere's law said is if I had a wire and I've got my current, I could have my compass, and my compasses would show that I'm actually, and if my wire is the current going this way, my magnetic field would be going around my wire in that direction. And that's Ampere's law. And in fact, if I wanted to write out Ampere's law, I'm going to just get that written out here. And basically, if we're dealing with the observation for Ampere's law, is that we're going to point our thumb along the direction and we're going to go around. And basically, that Ampere's law, they've actually described it in section 19.7. So one of the things that when we're dealing with magnetism is we're dealing with a lot of observations, all right? And one of the things that this experiment here, where if I take a wire and I have it in a magnetic field, now we saw that impact where it actually pushed the magnet down further. That actually was demonstrated by person named by the name of Orsted. And he actually showed that if I do this, my wire is going to bend one way. And if I do it this direction, my wire bends the other way. And so this actually demonstrates our right-hand rule as well as our wire going through this. And we get that observation that Ampere kind of puts together that we have that going in that direction. So we get these. So if I'm doing a wire, a couple of things we know that the sum of the forces is going to equal our force on our wire. And this force problem, this actual force problem deals with a single charge. But if I'm doing a current is a flow of charges. So if I'm looking at this setup here, where I have my field, I have a length of the wire in here that's inside the magnetic field, which is where I'm going to have my forces. And then the number of my charges is going to equal the number of electrons that we have per unit volume. And my volume, of course, is going to be the area of my wire and the length of my wire. So that's going to give me my number of charges. So if I do that, and I'm looking at my sum of my forces here, this gives me the sum of the forces is going to equal the number of charges. And then there's my charge because I'm dealing with my electron. I have my area and the length, and that gives me the number of charges. And then I have my velocity, and I have my magnetic field, and I have the sine of the angle. But if I have my setup like this, that sine of the angle is equal to 1. Now, back when we dealt with resistance and we defined current, we actually looked at this idea here, and we showed that this was the microscopic definition of current. So if I'm looking at my force now, if that's the microscopic definition of current, I'm getting the magnetic field. The definition of current, let me do it this way so we get it clear. It's NQAV. That was my definition of current. And this gives me my length of my item, but this was my definition of current. And so now I get the length of the wire, the magnetic field, the length of the wire times my current, sine of the angle. So its maximum, the force maximum is just going to be BLI as I'm looking at a single wire in my magnetic field. So we can do that. That's kind of an interesting thing to look at. So if I have a high power line, so here's my power line, and I have it between two power poles, and we have the Earth's magnetic field perpendicular, and my magnetic field, we're going to say, is equal to 0.500 times 10 to the minus 4 Tesla. And that gives us our magnetic field. And the length between these 2 points, we're going to say, is 36 meters. And we're going to say that this wire carries 22 amps. My force on that wire due to the Earth's magnetic fields is going to equal B times the current times the length times the sine of the angle. But because I'm perpendicular, that's going to be 1. So now I've got my 0.005 times 10 to the minus 4 Tesla. My current is 22 amps, and my length is 36 meters. And if I plug that into the calculator, I'm going to get something on the order of 3.96 times 10 to the minus 2 newtons. Now, we can compare this force with a gravitational force. And if I did that, we're just going to use our F is equal to the mass times gravity. I'd have to calculate the mass of my wire. And if I did that, let's just give ourselves a mass of the wire. And if I did that, I could do density times the volume of my wire. And if I did that, and I'm given 8.92 times 10 to the third kilograms meters cubed for copper. And then my volume of my wire is going to be 36 meters. And we'll do the area times my area of 2.5 times 10 to the minus 6. And if I do this, I'm going to get the mass is going to be something on the order of 0.803 kilograms. The gravitational force is going to be my 0.803 kilograms times gravity of 9.81 meters per second squared. And my gravitational force is going to end up being something on the order of 7.87 newtons. Now, we're about to do a calculation because one of the things that I think I've talked about on a couple of my other videos, if you've actually watched it, is that people worry about being under high power lines and looking at the magnetic field generation of a high power line. You know, how is that field? And we're going to see that here in just a minute. But I want you to look at the force that we've got due to gravity is significantly higher than our magnetic force that we have on this wire. And we're going to find out the same thing when we deal with what's the magnetic field being generated by current in a wire. But the reason that people get concerned about it is that there was a study done way back when. And it's one of those cases where the science in the paper was really, really good, but there was an error. And the error wasn't associated with the individuals doing the science. The error was associated with that there was a variable that they weren't able to predict, and they didn't find out about it until after the paper was published. So in Wisconsin, they had these two dairy farms. They had dairy farms across the road from each other. They had about the same number of cows. They got their feed from the same feed mill. They got the same number of grain. They got all the same things. But one set of cows was producing approximately 10 to 20% less milk than the other cows across the street. And the only apparent difference between these two dairy farms was that the cows that were producing less milk were under high voltage power lines. And so they thought it was the magnetic fields that was causing the reduction in milk production. Turns out that wasn't the case. There actually was a short in the milking barn associated with the farm that was underneath the power lines. When they fixed the short in the milking barn, which meant that the cows were getting a mild electric shock every time they came in to get milked, of course they're going to produce less milk than the cows across the street. And the cows across the street, when they fixed the barn, cows across the street started producing more milk, and the cows were equal. So there was no impact associated with the magnetic field. But the authors of the paper said, hey, we discovered that there was another variable and our conclusions were incorrect because of this other variable, and they actually retracted the paper. But nobody ever looks at the retraction of the paper. But the people who actually did the research weren't doing faulty research, were doing very good studies. They just had a variable that they couldn't predict. But it gives you an idea about the size of these forces that we're dealing with. So one of the things that happens is if we look at, and this is what we're about to kind of come into and we have to deal with. So if I have a magnet, so this is a bar magnet, and this is a North Pole and a South Pole. What we're going to do is we're actually going to create an electrical device, and one device will be a generator and one device will be a motor. And if I have a wire, and so this is one loop of my wire, and I have my magnetic field here, and if I look at my wire and I look at my magnetic field, so we've got a square wire, I have a magnetic field that comes through here. And if I have current flowing through the wire, so here's my current, we're going to get something that happens. So if I look at here, the force on this wire is going to equal 0 because I'm parallel to my magnetic field. The force on this wire is going to equal 0 because I'm parallel to the magnetic field. But this one is going to have a force that's going to want to move this one up, and this one's going to have a force that's going to want to move this one down. And the magnitude of those forces for both of these, if the length of my side is B, the force is going to equal the magnetic field times the current times B. That's actually the force that's there. But if I have an axis of rotation, and here's my axis of rotation, so this is B divided by 2, that distance is B divided by 2, what's going to happen is that, remember, the torque, the magnitude of the torque is going to equal my force times my distance. So this is going to actually equal my force times my distance, which is B over 2. So if I add up the torques, because I'm going to have these things and it's going to start to spin around, and I'm going to get a spinning around, the torque max is going to equal my magnetic field times the current times the area, and this is the area of my loop. Now, while we set this up for a square, so if I put this in and I have a current going in here, this is going to rotate around here, and I have just developed a simple motor. Oops. So no, I've just developed a simple motor. And you can actually go to Hobby Lobby and pick up a simple motor kit. And in fact, what it looks like is I have a battery in here that's going to develop my current. And I have 2 contacts here. And I have a series of loops of wire that go through here. And I have a little magnet that goes through this. And once I get it to start spinning, it'll rotate and I can actually do mechanical work. So you can get mechanical work, and it's related to this torque. Now, for one loop, this is what it's going to be. But for multiple loops, it's going to be the number of loops times the magnetic field times my current times my area. And that really gives us our quantity that's in here. And we actually, and if I go ahead and put this in terms of my angle, incorporate my angle here, we are going to define this NIA, and we're going to give it a mu, and we're going to give this a definition and call this the magnetic moment. But that magnetic moment is related to making my simple motor. This is just my simple motor, and it allows me to do that. And then we get those number of loops. And that's really important, as I said, for making a simple motor. Now, what we're going to see starting tomorrow is the reverse. If I were to use something, what's going to happen is Faraday's going to show. So what we have is Oersted and Ampere said that if I generate an electric field and I have a movement of an electric field, it will give me a magnetic field. And that's what they gave us. But Faraday is actually going to show that if I have a changing magnetic field, I can generate an electric field and go backwards. And so the same configuration, if I use mechanical work to do the spin, is going to generate current, and that's what a generator does. So motors and generators are very similar. One is giving me mechanical work, and one is using mechanical work to give me current. So that we get that. So what happens to us by using Ampere's law and this idea is that if I want to calculate the magnetic field from a wire, what that's going to end up being is our mu, and we're going to use mu here, and we're going to have our current, and then we get our 2 pi r, and that's the distance from the wire. Mu is considered the permittivity or the magnetic permittivity of free space. And this is going to equal 4 pi times 10 to the minus 7 Tesla meters amps. So if I get this number in here, so I can actually, so we could take that wire here, and we said that the current was 22 amps. And let's say the distance to the ground is 20 meters. We can calculate the magnetic field associated by that wire by 4 pi times 10 to the minus 7 divided by 2 pi, 22 amps, divided by our distance away from the wire, which was going to be 20 meters. And I'm going to get 2 times 10 to the minus 7. And I'm going to end up with 11 divided by 10. And I didn't pull my calculator out of my bag, so I'm going to have to do it this way. Okay, 11 divided by 10 times 2. I'm going to get 2.2 times 10 to the minus 7 Tesla. Pretty small magnetic field associated with a 22 amp circuit 20 meters above me. So you get that particular aspect. Now, when we do this, if I have 2 parallel wires, and these are separated a distance d, okay? And I have the current traveling both in the same direction. The force due to one, we'll call this force 1, and we'll force due to. The force due to 1 is going to equal B of 2. So whatever magnetic field that one is generating, the current in 1 times the length. But we just figured out what that B is. That B is my permittivity of free space. The current in 2 divided by 2 pi. The R is the distance between. I1L. And if that's D, I'm going to get mu 2 pi D I1 times I2 times my distance. And a lot of times we'll write that one out as F over L because that's my force per unit length. And I get my mu I1 I2 over 2 pi d. So you can actually work through those kinds of items. Now, when I do loops, so we did a square, but I can also do circles. And how I make a uniform magnetic field is we deal with something called a solenoid, and we do the number of loops. And if I do that, what'll happen is I'll get a uniform magnetic field on the inside of my solenoid. And that'll work out really, really nice. And our magnetic field inside our solenoid, which gives us our electromagnets, is the number times my permittivity of free space divided by 2r. And that's related back to the radius and that allows us to get our electromagnets. And that pretty much takes care of chapter 19. So, as I said, we're in really, really good shape on things. So, are there any questions? So, magnetism, just kind of giving you guys a heads up, magnetism is one of those more observational parts of physics. We don't do a whole lot of derivations because we're actually putting the equations based on the models, and we are putting that information together. Magnetism is one of those interesting little twists that happens, is that the observations for both electricity and magnetism came long before the mathematics that we use to associate with them. Okay, questions?